Hello everyone. In the last session, we looked into elasticity in solids, where we discussed about stresses, strains, and their relationship using the D matrix, which is the constituent matrix. We also discussed about true stress and true strain curves, and then we moved into two-dimensional problems, where we discussed about plane stress and plane strain elements. Now today I won't be going through chapter 4 because it is a lengthy chapter, and I will do that right at the end of the sessions. We're going to look into chapter 5, which is on finite difference method. I'm not an expert on hydrology. I only have limited knowledge on it. So if I do some errors, please do indicate in the comments below. I'll be focusing solely on the concept of FDM and how they are used numerically to solve the partial differential equations by using finite difference equations as their approximations. Finite difference method is a type of numerical method which is used to solve problems related to partial differential equations. Basically, what we do here is, if you have a differential equation like this, we approximate such an equation as numerical differential form like this. As we all know that this is slope of a curve of function u, and this is also slope of a graphical representation of the function u, which is dependent upon x. For example, let's say we have x and u, which is a function of x, and this function u, let's say when you plot it, looks something like this. Now if we want to find a slope at any point, let's say here, then it will be tangent. This is our slope, du by dx. Let's say at certain point xa, at xa, this will be our slope. These are the values in the x-axis, these are the values in the y-axis, which is itself a function. Let's say this is, then if you want to find a slope of du by dx around here, then what you have to do, take x4 and x3 and find the slope, which will be given by, now you can generalize this kind of equation as dy by dx, which is slope at a certain point, can be approximated as where this I here is the number of discretization of small lengths. Let's say this is delta x between each grid line. So the I here can start from 0, 1, 2 and go to n number of discretizations. Depending upon how many grids you have, your delta x can vary as x divided by n. Therefore, in this graph, you can have n number of grid lines like this, where each spacing will be given by your total length divided by number of grid lines, and n is number of discretizations of the length x. Generally, what is done here is we use Taylor series to approximate finite difference equations to partial differential equations. For example, Now Taylor series of y x plus delta x will be given by, if we assume the higher orders be represented by a term te, then our Taylor series will be, now the term te is known as truncation error. We can assume the higher orders to have negligible effect in this solution, therefore te will be 0. So our dy by dx now will be given by, since we have used plus sign here, which means that if you have a grid like this and you are here, that's your x. Now your x plus delta x will be somewhere here. Therefore we are moving forward in the x direction. Therefore this approximation here is known as forward difference approximation. Again, what you can do here is we can move backwards in space. Here this will be your x minus delta x. Now you can use similar expansion of Taylor series here by taking this negative, so this one will also be negative. Therefore what you'll get is, now here, since we are moving backwards in space, this is known as backward difference approximation. Now what you can do here is we can add these up and write it down here. So you get 2 dy by dx equals to, when you add this you will get y x plus delta x minus y x minus delta x. Now when you take your 2 here, you'll be left with 2 delta x. So this is our another equation to approximate the partial differential equation. Now this is known as central differential approximation. You can see here that in this graph we are taking this and this point for our central differential approximation. Now as you can see here in the Taylor series, truncation error will decrease if we include the higher orders. For example, if we take y x plus delta x equals to yx plus del x dy by dx plus delta x square by 2 factorial to y by dx square t2, your t2 will be equal to te minus del x square by 2 d2y by dx square. Therefore you can see here that our truncation error decreases if we include higher orders in our approximation. Now this was about one-dimensional space. If we want to look at a two-dimensional space where you have x-axis here, time axis here, let's say your flow is dependent upon space and time. If you recall hydropower fluid mechanics or hydrology books such as from Vente Chow, or you can look into Victor Miguel Pons books, and you can observe that your flow, this is your flow, this flow can be within a pipe like this, like a water pipe, or it can be in an open channel, like this. This can be your flow. So your flow will depend upon x in space and certain time of the day. At some times the flow may be high, at sometimes the flow may be low. For example, in wet season the flow will be high. However, in summer season, in dry season, the flow will be less because there will be less rainfall. Let's take this as time and this as our flow. Your flow will depend upon xt plane. So you may get a 3D curve that looks something like this. Not sure, but now in finite difference method what we are doing is we are taking xt plane, which is this plane here. Here x will be a point in space, certain location in a channel or a river at certain time of the days. So you have t as well. So this is, let's say this is our certain location on the path of the river along the channel, and t is the time of the day. It may be hours or minutes. Now in FDM what we are doing is we are looking into this plane here, xt plane. So when you take this plane out, you can plot it, and this plane, as you can see here, will have different grid lines like this. This can be x1, x2, x3, x4, x5, and from here as well, which can be t1, t2, t3, t4. So what we're doing is we're taking this grid and drawing it here. Let's draw it. So this is our grid. Basically this point here, which is the origin, if you take a channel like this, let's say to a depth of h, and this is our flow q, this is length l. Now here this is your origin where x equals to 0, and here your x equals to, let's say, L by 4. Here your x equals to L by 2, x equals to 3L by 4, and this here at the end your x equals to L. Now this region here where you can observe water flowing in is known as your inflow, and here you can see your water will exit. Now this location here is known as outflow. Once you know inflow, which is the initial condition, the target here is to find our outflow here at the length L. So our outflow Q at L at certain time t equals to what? Given you have an inflow, you have something inflow which is 0 comma time t, let's say this is time in, equals to something. So your target here is to find your outflow. Now to find your outflow, this is similar to FEM. If you discretize this into smaller grid lines, 1, 2, 3, 4, into 4 parts, then your each part, your delta x will be equal to L by 4. But you can discretize this length into many number of small segments like nodes in FEM. We can discretize L into 100 small sections. So your delta x will be L by 100. Now these grid lines here represent such division, so that's discretization. So this is your delta x. So each of this will be your delta x. Similarly, you have to discretize your time as well, delta t as well. There is a way to determine what delta t should be based on your delta x, which we will talk about later. In this grid, we can be given flow at this point. So that is at x2. Your x2, let's say, is, this is our x1. x2 is L by 2. So let's say you are given your flow here, q1, at certain time t1, and then you're also given at certain time q2, maybe here as well, q3. Let's say you know what are the values here, here and here are. Then your target may be to find your flow here at time. This is t1, this is t2, t2. So your flow at x3, which is this one, the x3 at time t2. Or your target may as well be to find what is your flow at x4 at time t1. Now there are several schemes to solve this problem. One of the scheme is known as implicit scheme. Let's say you have differential equation that you approximate this one based on variables in future. For example, let's say you know the value of q at x equals to x2. If you represent your finite differential equation like q at x3 at time t3 minus your flow at x2 in time t3 divided by your delta x, then this type of scheme to solve your problem is known as implicit scheme. Now for the explicit scheme, when you represent your FDE like dq by dx as, where you know q at x equals to x2, this is known, at x2 and t equals to t2 are known, and here x equals to x2 and t equals to t2 are known. Now if you represent this finite differential equation in the form, then such a scheme is known as explicit scheme. So you can see here that in the implicit scheme we know flow at x equals to 2 and t equals to 2, but we are using t3 to approximate our finite differential equation. In the explicit scheme, you can see here that we have used t2, which is known, which is at the current time, and this is in the future. Similarly, you can have your forward difference approximation, backward difference approximation, and central difference approximation based on your values in the future or at the present. Now let's look into kinematic wave models. There are different types of waves. The simplest kind would be kinematic wave. The other two types are diffusion wave and dynamic wave. And this is the most simplest and this is the most complex. If you look into momentum equation in conservative form, which should look something like this. This is the momentum equation. Now here, this term is known as local acceleration term. This term here is known as convective acceleration term. This term here is also known as temporal acceleration term, because this term here, you see here, this is a differential of time, so this is the acceleration that is dependent upon time. Now here, this equation, you can see it is a derivative of x, so this term here is dependent upon space, which may be x, y and z. Now this term here is the pressure force term. This term is the gravity force term, and this term here is the friction force term. You can look into some books related to hydrology to understand this equation. Here, Q is the discharge at a certain cross section of a channel, like we did before. If this was a channel and you have water flowing, and at certain location x, if you take the cross section like this, you'll have water up to here which will be flowing. So this is a discharge flowing at this cross section x. Now A would be the cross sectional area which is this. S0 is the slope of the bed. For example, if this was a channel which was inclined at a certain slope, this slope would equal to S0. And let's say your water is flowing at this level here. Now this slope, the slope of the water here, which is SW, is nearly taken as slope of the bed. Your water will be flowing from here, which is the inflow, and exiting here, which will be the outflow. And you may have storage here. In cases of reservoirs, if this was a bed slope and you have your dam here, the water may be filled up to here. Now this will be the inflow, and when this is full, this will be the outflow, and you'll have some storage. This is reservoir, this is channel. Now SF is the slope of energy and G is the acceleration due to gravity. Now this equation can also be written in non-conservative form, which is, as I mentioned before, there are three kinds of waves. Now in here, if you take only these two terms, then this model will be known as the kinematic model. If you take these three terms, then this will be known as the diffusion wave. And if you take all of them, then this will be known as the dynamic wave model. So you can see here that the simplest kind of wave model will be the kinematic wave model, where you will only have the gravity and the frictional term, which will be equal to each other. Let's say you have x, y and z plane, where water would be flowing like this, and in here we can take a small cube. Let's make this cube bigger. So we are looking into very small cube section in 3D. This is dz, this is dy, and this is dx. And velocities in these directions can be represented as u vector, v vector and w vector. Therefore, what you can write here is your acceleration ax in the x direction will be given by du by dt. In the y direction will be given by dv by dt, and in the z direction will be given by dw by dt. Now if you want to expand this, we have to use partial differential equation on this one using the chain rule. What you'll get is, because if you are looking at velocity, your velocity is dependent upon x direction, y direction, z direction and time t. So there are four variables. Therefore, we have to form a partial differential equation consisting of all these variables here. Now dx by dt, dy by dt and dz by dt are the velocities along x direction, along y direction and along z direction. Therefore, what you can write here is, you can see here that these terms here are space dependent, so are known as convective accelerations, and this part here, which is dependent upon time, is known as local acceleration or temporal acceleration. Now if you take this section out, which will look something like, or you can take it as a pipe like this, where you'll have water flowing from here and exiting from here. Here also you can have water flowing in here in the pipe and exiting from here. Let's say this section 1, this section 2, here also 1 and 2. And now if you look into the principle of conservation of mass, which states that your outflow minus inflow must be equal to change in volume. The volume of outflow and the volume of inflow will be given by, either flow at section 1 is denoted by Q1 and section 2 is denoted by Q2, then your outflow will be given by, inflow will be given by, now this term here is in volume per second times second, so you'll get volume here equals to change in volume. Now here, if you take a small distance delta x, small length, then you can take a volume, small volume like this. Let's say this is area A1 and here area A2, and you take a small distance delta x, then the volume here will be given by A1 delta x, and volume here will be given by A2 delta x. So your change in volume will be A2 delta x minus A1 delta x. Now I can write this as Q2 minus Q1 delta t equals to A2 minus A1 delta x. You can write this in differential form as, now this is known as continuity equation. Now you can solve this numerically by approximating this and this like we did before, like these here. So you can approximate these partial differential equations using finite difference equations. Your dq by dx can be written as, if you have a channel like this, this will be one section, section 2, and so on, x1, x2, and you also have time dependent variable t1, t2, t1, t2, t3, and so on. Then you can use either backward or forward approximations. So let's use backward approximation in this. So we can write this one as q as, let's say, x2 at time t2 minus q at x1 at time t2 divided by delta x. Let's say q at x1 t1 is known, but we are using t2 here, therefore such a scheme here is known as implicit. And also there are many formulations on the flow of the water, such as that of the Manning's equation. If you look into the uniform flow in open channels, then what you'll get is your flow is given by 1 by Manning's constant times area times hydraulic radius to the power 2 by 3 into frictional slope to the power 1 by 2, where this is Manning's coefficient. Your R is given by area by weighted perimeter, which is, if you have a channel like this and water flowing like this, let's say the width of the channel is B and depth of the water is Y, then your weighted perimeter is this part here, the boundaries of the channel which are wet or which are covered by the water. So this will equal to B plus 2, Y equals to weighted perimeter. In a wide channel, your weighted perimeter can be approximated by B. If your channel is so wide and your depth of flow is so small, then your weighted parameter will be approximated by the width of the channel. For simplicity, what is done is your Manning's coefficient, your frictional slope, and your weighted parameter are taken to be constants. Now, your area in this formulation is a function of flow, which is given by this formula, where alpha equals to, but this is slope of the bed, and your beta will be equal to 3 by 5 equals to 0.6. Now you have your alpha and you will have your beta. Since you have an equation for area, your dA by dt, which is required here, is given by derivative of this term with respect to time. Now what you can do is you can have this equation in terms of Q, and you can use this equation and formulate another equation. So what you'll get here is dq by dx plus alpha beta q beta minus 1 dq by dt equals to 0. Now to solve this, what you do is, as you can see here, there are two parameters, there are two variables, x and t. So we make a grid line like this. This is x, this is t. Now in the channel, let's say this is section 1, this is section 2, and you'll have time variable at t1, t2, t3, or you can write this as at I plus 1. This one will be z plus 1, z plus 2, and so on. So if you write this in the graph, what you'll get here is I plus 1, that's a grid number, and here this length is small del x, so this will be equal to your del x, and here this will be equal to delta t, and you can write here grid line j and grid line j plus 1. In time we have to move in the future, we cannot move backwards. Now let's say you have a graph which is time and your flow q. It may be something like this, and let's say this is t1 and this is t2. Let's say this is inflow curve, which means that if the inflow was happening at section 1 here, then this curve will give us the value of q at certain time t at location x1, or you can say at I here. So if you have this curve, then you can find your point here, so that is at time t1 and at time t2, or z plus 1, and let's say you know what is the outflow at time t1, which will be q2 at time t1, which means you know your value of q2 at x2 comma t1. Now this is I plus 1. Now this is j. Now I can plot this one here, and you have to find what is the flow, what is the outflow here, which is q at x2 in time t2, which is unknown. You have to find it out. Or you can say this one as q I plus 1 j plus 1 equals to what? The subscript is the grid number in the x-axis, and this is the grid number in the time axis. Now to do this, what you have to do is you have to substitute these partial differential equations into finite difference equations as done earlier. So your dq by dx will be equal to, we can use implicit scheme. So this is the backward approximation using Taylor series as we did earlier. Similarly, your dq by dt will be given by, now you can see here that this point here is this point, this one is this point, and you have delta t. Here in time we always have to move into the future step. Now we have found dq by dx, dq by dt, but we have to find q. Now for q, what to do is we generally take the average. For this point, let's take average along this diagonal. So what you get here is q equals to, so this will be our q. So we also have our q now. Now what I can do is substitute these values back into the main equation, this one. So you'll get the point we have to find here is this one and this one. So when you solve it, when you take the common and you solve it, what you'll get is, so this is your main equation to solve the value of flow at x equals to I plus 1 and time t equals to j plus 1. Now this is a linear scheme. This is linear. Now if you want to look into nonlinear scheme, then what you have to do is you have to find dA by dt, this one, directly rather than using this equation. So now here you have to find values of your area at different sections of the channel in different times independently. So what you'll get here is AI plus 1 j plus 1 will be equal to alpha q I plus 1 j plus 1 beta, and your a I plus 1 j will be equal to alpha q I plus 1 j to the power beta, and then you substitute these values back here. then you'll get, now this equation is a nonlinear equation in Q I plus 1 J plus 1. Therefore, we have to use certain iterations to solve this problem, or you can use Newton-Raphson method to solve your equations. And let's say you obtain a solution of a problem. Let's say this is the exact solution that you were after. You may get a solution something like this. Now you can see that there's difference in the amplitude. This is your numerical solution. This kind of error is known as diffusion. Similarly, you may get a solution which may look like, you can see here that even though the peaks are same, they occur at different interval. Now such types of error are known as dispersion errors. The accuracy of your numerical scheme depends upon the order of the finite difference equations you have taken into consideration. For example, if you use forward or backward, which only have first order accuracy, then in such cases you'll get both dispersion and diffusion errors. If you use central finite difference equations, which are second order of accuracy, you'll only get dispersion. If you use higher order of FDEs, your error also minimizes. Now if you use FDEs of third order accuracy, then there will be no dispersion and no diffusion, but they take longer to solve. Your errors are basically dependent upon the number of grids. So to reduce this error, either you have to use finer mesh or small spacings or discretizations, or you have to use higher order discretization schemes, which may be the third order one. Now let's move into another section which is known as hydraulic channel routing. Now this channel routing is used to analyze the effects of a channel on a hydrograph peak flow and travel time. Now what happens is that when you have a channel, in a channel may look something like this, and you'll have your water flowing like this. There can be pebbles, there can be some grass growing here, and this will be your inflow, this will be your outflow. When you have a hydrograph traveling along the length of a channel, the feature of the hydrograph may change depending upon the channel's resistance or storage characteristics. If you look in a plan like this, and let's say you have a river flowing like this, in this region you may have some inflows. In this area 1, let's say your peak flow is Q peak 1. Now as you see here, there are no lateral inflows, which may result in drying of the channel and may result in attenuation of the peak. So here your Q peak 2 may be less than Q peak 1. In such type of channel, if you are provided an inflow hydrograph, then your objective would be to find the outflow hydrograph. Now there are several methods for channel routing. Now here we'll just use simple method, which is the Kinematic Wave Model. In this case, your outflow at section 2 will be given by C0 inflow at section 2 plus C1 flow at 1 plus C2 outflow at 1, where C0, C1 and C2 are known as routing coefficients, where C0 will be equal to C minus 1, 1 plus C. C1 will be equals to 1 and C2 will be equals to 1 minus C divided by 1 plus C, where C equals to small c delta t by delta x. Now C here is known as celerity speed C, and in the Manning's equation C is equals to 5 by 3 velocity v. Now this is for wide channel. If you don't have a wide channel, then your small c celerity speed will be dependent upon slope of the rating curve, which is dq by dy divided by t, where t is the top width of the channel, y equals to stage or depth, and q is the discharge. So this is how you obtain your celerity speed, and this term C is known as Courant number. Now we solve the problem using Courant number 1. Then what you may get would be, if this was the inflow, then you may get something like this for C equals to 1, where you'll have some error, which is the diffusion error. And let's say if you use c greater than 1, you may get a curve that may look something like this. Now here you will see that it has some negative flow. This is a QT curve, which is not possible. Therefore, generally we select our delta t and delta x such that our current number equals to 1. So that's the limit on it. That's how we define our time step and our spatial interval. If c equals to 1, then you can see here that c0 equals to 0, c1 equals to 1, c2 equals to 0. Therefore, your outflow will be directly given by c1 I1, that equals to inflow. So outflow equals to inflow. Therefore, these two curves should match up. But due to diffusion, you'll get some error. And here, due to dispersion, you'll get this kind of error, which is unrealistic. Now, let's move into the dynamic wave model. There are two schemes here which are used to solve a dynamic wave. The first method is the Pressman's scheme, which is implicit 4-point scheme. Here in this grid, let's say this is I plus 1, this is dx, let's say this is j plus 1, j, and this is dt, and this will be 0.5, and let this be chi, and this be 1 minus chi. Now in this method, we'll use 4 points to determine our derivatives, which are these points here. Here, your dy by dx will be given by this is a non-derivative term. Chi is known as weightage term. We can have different values of chi. If chi equals to 0, then this will be known as the fully explicit scheme. If you assume chi equals to 0, then your y can be directly obtained by half of this plus this. If you use 0.5, then this is known as box scheme. If chi is used as 1, then this is known as fully implicit scheme. When you put chi equals to 1, this will be half of, see here, these terms which are in future. Therefore, if you use chi equals to 1 here, this term will be 0, and the remaining part will be the implicit part here. Chi equals to 0.5 to 1 for a implicit scheme. If you use something like this, then what will happen is that your continuity equation will look something like this. So what we did here is we substituted y here by a, so we obtained dA by dt and wrote it here, and this one y by q, so you obtain dq by dx and substitute it here. Now this will be your moment continuity equation. Similarly, you can obtain your momentum equation as well. Your dq by dt, as you obtained dA by dt earlier at the top, and substitute your y equals to q squared by a in the above equation and obtain your this differential equation. Similarly here as well. Now this is your non-differential term. Now this one will be given by this y here, which is a non-differential term. Therefore, if you have channel length like this, let's say you have discretized the length into n grids, which means that you will have n-1 steps, or you call it as reaches. Now you can see that in each reach there will be two equations. One is this one, other one comes from here. Therefore, in total there will be two n-1 equations for n grid lines. Therefore, we are too short to solve for all the values in the grid points. Now the other two equations are obtained from your boundary conditions here and here. So we get two more equations from boundary conditions. Therefore, you will have 2n-1, 2 plus 2, 2 in equations, and you can solve for the unknown points in the grid. Similarly, there is another scheme which is used for the dynamic web model, which is known as the LeapFrog method. What I do here is we use central difference approximation equations rather than using the forward or backward differential equations. Therefore, in this scheme we'll have three grids at a point I, -1, I plus 1, j, -1, j, and j plus 1. This is delta t and this is delta x. Now here what we do is we take points, we take this point and this point, and here we take this point and this point and apply central difference equations. So here what will happen is that your dy by dx will be given by, so here we are taking this point and this point, and for your dy by dt you will get, so here we are using this point and this point, and your y can be taken either as this point here, which is y ij, or as an average of these 2 points, which will be equal to, or as an average of all of these 3 points. So you'll get 3. So for y, you can use either of these equations. Now what happens here is your continuity equation, which is given by dq by dx plus dA by dt equals to 0, will become equal to, you'll have your momentum equation as well. Now you can use the similar procedure, and finally you'll get q I j plus 1 equals to q I j minus 1. You can try substituting these terms in place of y and get this equation. So this is how you solve for our q. Now let's look at an example here which will make things really clear. Let's say you are given a channel section like this, which has a slope of, let's say, 0.01. Let's say the width of the channel B equals to 40 meters, and in this channel you have your water flowing, and for this channel section your Mann's coefficient is 0.040, and the total length of this channel be 5 kilometers, and delta t, the time interval, be 1 hour. Now the problem might be to develop a kinematic wave model for the given data below. Let's say you are given a grid like this, where this is I plus 1. This can be taken as 1, so this will be 2, which is x. Now your delta x, let's say you are given to solve your problem with a single reach, which means that you have to take your delta x from here to here. That means it will be 5,000 meters. So delta x equals to 5,000. Now this is your time axis, where this will be t1, t2, t3, t4 equals to 1, so j equals to 2, j equals to 3, j equals to 4. Now in this grid you are given these points here, which are the initial conditions. So this is at 0 meter, this is as 5,000 meter. So this is your initial condition at time t1, t2, t3, t4. So your time can be, let's say this is at 8 AM. So after 1 hour, your delta t is given as 1 hour. So this will be at 9 a.m., at 10 a.m. and at 11 a.m. So your delta t equals to 1 hour. So when you measure the flow at section 1, which is, let's say here, which is this one, this is section 2. So at 1, when you measure your flow Q at 8 a.m., 9 a.m., 10 a.m. and 11 a.m., what you found was these values were 70 meter cube per second, 100 meter cube per second, 100 meter cube per second, and 100 meter cube per second. And at end 2, you measured your Q at 8 a.m. and you found out that this was equal to 70 meter cube per second at 8 a.m. Now your problem is to find what is Q, what is the flow at 9 a.m., 10 a.m. and 11 a.m. So at this grid, this one will be 70, 100, 100 and 100. Here at this point here, which is 8 o'clock as section 2, this equals to 70, which is the outflow. Now you have to find this point, and this point. So Q2 at T2. So Q, you can write this as Q3, Q23 and Q24. So Q22, Q23, Q24 equals to what? Now you can see here you are given your Manning's coefficient. Now your beta for Manning's equation is 0.60 as you did earlier. Your alpha is given by this equals to 0.04 times P. Your P is for a wide channel, your P can be taken as B, therefore this will be 40 to the power 2 by 3, 1.49 times root under 0.010. This to the power 0.60. Now you'll find your beta value here. I'll do this in Excel and I'll upload the Excel file, and then for the kinematic wave model as we derived earlier, let's see, for your Manning's equation, what you have here is this one here. So I'll copy this down. Now here we'll substitute our values. So your Q I plus 1 J plus 1 will be equal to delta T. Your delta T is 1 hour, that is 3600 seconds, divided by 5000. This will be Qi J plus 1 plus your alpha, which you calculated earlier, times beta, which is 0.6, times, now you can see here your I varies from 1 to 2 and your T varies from 1 to 4. Therefore you have to find your flow Q4. So for this equation, let's take an example. Let's say we put I as 1 and J as 1, which means that This will be Q12. This will be Q21. This will be Q12, Q21, Q12. Then, as you can see above in the graph, we are given this is Q11, Q12, Q13, and Q14. So from here, Q12, Q13, and Q14 are same. So Q12 will be equals to 100. Q21, which is this one, equals to 70. Q12 equals to 100. Q21 equals to 70. Q12 equals to 100. You know your alpha, you know your beta. Then what you can find would be Q22. After you know Q22, then you can do a similar procedure and find this. And then do similar procedure and find this. Let's do our problem in Excel now. Now this was our problem. Now we are given del t, del x, or del t is given as 1 hour. So this equals to 3600 seconds. Del x is given as 5000 meters. Now for the channel, we are given width of the channel, width, which is b, as 40 meters, and we are given our bed slope S0 as 0.01. We are given Manning's coefficient n as 0.04. Now we have to find beta. For Manning's equation is given as 0.6. Now we have to find our alpha. To find our alpha, we have to use this equation here. Now this will equal to n, with here n times p. Let's take p as b, assuming it to be a wide shallow channel. So we get our p to the power 2 by 3 divided by 1.49 into the square root of S0. This is our S0 to power of beta. So this is our alpha. After this, we have this general equation to find our flow. For this, so let's say this is time axis, this is our x-axis, where the points here are j, are given by j, here are given by I. So j, 1, 2, 3 and 4, because there are 4 steps in time, t1 to t4, 8 AM, 9 AM, 10 AM and 11 AM. So right here, this is 8 AM, 9 AM, 10 AM and 11 AM. For I, this will be 1, this will be 2. This one here is at 0 meters and 2 here is at 5000 meters. Now Now we are given this value here, which is at q1, 1, which is 70. This one here is 100, this is 100, and this is also 100. This is given as 70. Now we have to find these values here. So this is a table for q I plus 1, j plus 1, or q x, t. Now to find this one, we have to use this equation here. For this, what I'm going to do here is I'm going to find separate values for them. So numerator, let's say you have to find this one. This is your q22, right? This is q22. This is q23, and this is q24. To find q22, you have to put I equals to 1 and j equals to 1. So here I equals to 1, j equals to 1. Here I equals to 1, j equals to 2. I equals to 1 and j equals to 3. So for numerator, this will be equal to delta t divided by delta x times q12. q12 is 100 plus alpha into beta, alpha into beta into alpha. This is our average. So average of q21 and 12. This is our 21 and 12. So this is our numerator, and we also have to find our denominator. I'll just copy this because they look like. So we don't need this one here. Alpha into beta, average of this and this to the power beta minus 1. So this is our beta minus 1. Now this is our denominator, this is our numerator. So this value will be equal to this numerator divided by this denominator. We get 188.0662. I can just copy these here, which will give me values of numerator for this case here. So I can just click like this and obtain our values. This is our solution. So therefore, what you can write here is your q22, q23, q24, this will be equal to this one, equal to this one, and this will be equal to this one, meter cube per second. Here, let's see what happens if I decrease my del x. Let's make it 100. See here, the value is close to 100. Generally, what will happen is that your inflow for a small step is nearly equals to your outflow. So let's say if this is 1 meter, see, it's nearly equals to 100. If I make it 5000, which means that I'm solving this directly by using one step. This is very crude analysis, as we know that to make it stable, current number should be equals to 1. Now our current number is given by this equation here. So let's say if you are not given your time step, but you are given your speed here, let's take it to be 5 meter per second. You have to assume c to be 1 and obtain your delta t by delta x ratio. So delta t by delta x ratio would be equal to 1 by 5. So you have to make this one 0.2. So you have to change this. So this will be equal to this times this. So you get our step time delta t as 1000 seconds, and you have to solve your problem. So in cases when you are not given time step or your spatial step, then you may be given celerity speed, from where you have to obtain your del t by del x required ratio, and then you can assume your del t and del x to have the same ratio and solve it like this. So let's move this one back to our original case. This one was 3600, and this was our solution here. So this is it for today. If you want to look into how momentum and continuity equations are obtained, please refer to one of the books or your notes from previous years on hydrology, fluid mechanics, or hydropower engineering. I'll be uploading this Excel sheet together with this video. You can download this sheet and look at it. Please inform if you find some mistakes here. In our next session, we'll look into chapter 6, which is on method of characteristics, and we'll try to do numericals on that chapter as well. See you next time. Bye bye.